All right, so let's go back to our problem. Our problem, last time we ended up with this. I would like to write it with bold. CXXW, that's our best W, the one and only I want to find, is equal to lambda W. And okay, good, I learned W, the best W direction that gives us the minimum reconstruction loss is an eigenvector of the covariance matrix. What's wrong with my reconstruction? Anyway, covariance matrix CXX. But which one? Which eigenvector? Because we saw recently that there are n, like 63, so there are 63,000 eigenvectors, 63,000 eigenvalues, like which one? So in order to answer that, I'm going to go, since I know this is the eigenvector, I'm going to copy, where's my copy tool? I'm going to copy our error. So that's my error. And I'm going to copy, and I'm going to go and write it here. Paste. Okay. Paste. Perfect. So this is my error, remember? And if my CXX is so if I can right now replace this CXXW in the best case scenario CSXW is equal to lambda W, right? So if I can go ahead and replace it, my error then becomes 1 over n summation I equals 1 to n x of I transpose x of I. So that's a term that I cannot reduce. Like that's a part of my data set. Whatever I do with my W, it is going to be there. Minus W transpose, instead of CSXW, I can write lambda W plus lambda W transpose W minus lambda. So my error then becomes 1 over n, this term that's always going to be there, x of I transpose x of I. And these guys are going to like nicely cancel each other. So I'm going to get minus lambda. So this term has nothing to do with minimization. So if I want to minimize error, it means that I need to minimize negative lambda. It means that I need to maximize lambda. Okay. And what was lambda? Lambda is an eigenvalue of CXX. So the best of the bestest direction. So the best direction, therefore, let me make it bold, green. So the best W then is the eigenvector of CXX corresponding to the largest. Why? Because I need to minimize error, maximize lambda eigenvalue. All right, so that's that deserves some exclamation marks. And this is, my dear friends, so this guy is called the principal value. So that's not principal value, principal component. So we have the principal component that corresponds to the largest eigenvalue. All right, so that's one. What about the next one, right? So I would like now to ask this question: what about other dimensions? So I found myself some W. Now I would like to call it, I know the best direction is the one that corresponds to the largest eigenvalue. So best direction to project your data onto is the eigenvector of your covariance matrix that corresponds to the largest eigenvalue. So that's principal component, right? So the other dimensions, I want my other dimensions to be one, to like also minimize the reconstruction error. So I would like to minimize some error, but this time, again, the same thing. I would like to have x minus x hat square, but this time my x hat is w1 z1 plus w2 z2, right? So these are, I have my two directions right now. So again, I want my w2 to be also unit vector, and 3 now, based on the last thing that I want here, you remember all the things that I have, each dimension in the new representation introduce something new. I want it to be some new dimension. I want it to be orthogonal if possible. W1 transpose W2 is equal to 0, right? So that's what I want to minimize. So if I were to minimize, if I were to write my error now, which is equal to, again, 1 over n summation of all I equals 1 to capital N, but this time I'm going to write x of I minus, okay, my next one is something like this. So W1 Z1 plus W2 Z2. Okay, so that's my new thing. Plus, I know my lambda, I'm going to call it lambda 1, W1 transpose W minus. Whoops, what am I doing? Lambda 1, W1 transpose W minus 1, plus, I want the second one to be unit vector 2, so I have W2, lambda 2, W2, W2 minus 1, and plus I want them to be unit norm, right? I want to minimize, I want to make them orthogonal, W1 transpose W2. Okay, so that's what I want. And let's go ahead and rewrite the same thing, and we will get this. So I have 1 over n, I equals 1 to n, x of I minus W1. What is Z1? Z1 is the direction on W1. I know I was very happy with W1. I know W1. W1 is the best one. So I have it in my pocket already, and I would like to find the W2. And from W1, W2, I will find W3, and I will keep going, right? So I am making everything like my directions orthogonal right now. I'm fighting collinearity, right? So I have my W1 transpose x of I minus W2, W2 transpose X of I transpose X of I minus W1, W1 transpose X of I minus W2, W2 transpose X of I close parentheses plus lambda 1, W1 transpose W1 minus 1 plus lambda 2, W2 transpose W2 minus 1 plus lambda 3, W1 transpose W2. Okay, so there are way many terms in this one, but the good news, let's go ahead and when we do the multiplication, right? So I'm going to distribute. But when I distribute, some of the terms have nothing to do with W2. I know I'm happy with W1. So right now, let's go ahead and decide on like never to write, never to bother about the terms that have no W2 in it, right? So if I were to multiply, so W1, so X1, X1, this has nothing to do. So I'm writing the red one, red color, nothing to do with W2. I'm learning W2 right now. So X of I, W1, W1. So that's, I don't need to calculate 2. I will have to calculate this. So this guy will have W2 in it. And again, this for the second one. So W1, that was a W1 here. I forgot. So this term, I don't have anything to do. I will have to calculate this term. Perfect. And I will have to calculate every term that's here. Okay, so I eliminated 3 of them. And I can go ahead and eliminate this one too. So let's go ahead and write what we have. So I have 1 over n, I equals 1 to n. So I have X of I transpose W2, W2 transpose X of I. Now it's going to be simpler for me because I know what this is. This is going to be, again, it's going to give me W2 CXX W2, right? So it's not going to be surprising. For the second one, I have one term here that starts from this guy that's equal to, not equal to, plus. So I have minus actually 1 over n. So I'm doing the second one. I equals 1 to capital N. Let's do this one. So I have X of I transpose W1 transpose W1, and it goes to W2. Whoops. Sorry, I had to take the transpose of this. W1 transpose W2, W2 transpose X of I. Okay, so I have this. The next one, I go minus here. It goes to this one. Minus summation I equals 1 to n. X of I transpose W2, W2 transpose X of I. Perfect. This one goes to, again, plus 1 over n, summation I equals 1 to n, X of I transpose W2, W2 transpose W1, W1 transpose X of I, and again, another plus here, 1 over n. Wait, let me make sure that this is accurate. Well, yeah. Okay, I guess this should be also plus because here when I'm calculating this, I'm coming from here to here. So negative times negative is positive. 1 over n, I equals 1 to capital N. Now I'm doing the last one. X of I transpose W2 W2. W2 transpose W2, W2 transpose X of I. Plus lambda 2, W2 transpose W2 minus lambda 2 plus lambda 3, W1 transpose W2. Okay, still looks a lot, but I have some good news for you. Let's please look at this guy. W1 transpose W2. It's a summation, but I know that these two directions are orthogonal, and so this whole summation disappears, right? Again, I have the same thing here, so this is all 0, and this summation disappears, and here this one doesn't disappear, but this is equal to 1. So what I will have is eventually this guy is going to cancel. So these two guys are going to cancel each other. And this guy is going to go. This guy is going to go. Eventually, what I will have here is equal to 1 over n. I already eliminated the one with the excess. So I have this term right now. Can I write this as W2 transpose CXX W2, please? Right. So again, I have so these guys cancel each other. I'm getting there. W2 transpose CXX W2. Okay. This canceled. This becomes 0 because this guy. Let me use the laser. So this becomes 0. This guy because they're orthogonal, right? This also becomes 0. These two guys cancel each other. They're the same thing. So all I have the first term plus lambda 2 W2 transpose W2. This term is going to be 0 when I take the derivative 2, plus lambda 3 W1 transpose W2. Okay. It would have been great if I didn't have this term, but this last part, but it is the last part that made all of the cancellations. Remember, I have to have it such that I have all of these zeros. So the last term, if it weren't for the last term, I would have said, well, it's another eigenvalue. Sorry, another eigenvector. So if I take, so W2 star then is at the optima of this cost function, which also minimizes the reconstruction error of this new introduction, this new dimension that's introduced. That's also unit variance, which is orthogonal to the first direction, which was the best direction that minimizes the error, which was the eigenvector that corresponded to the largest eigenvalue of the covariance matrix, right? So if I take, I would have wait. I must have one of the negatives. Well, okay. So this guy, apparently I forgot the negative here. Right. Okay. So let's make sure that I forgot the negative here. So this is what I'm calculating. So there's a positive and there's a negative. So that's why it has to be negative. Perfect. So I get 2 negative 2 CXX W2 plus, well, 2 lambda 2 W2, okay, plus lambda 3 W1. All right. So that's what I get. That's not W star. That's W2 star is at when this is equal to 0. So I'll have to solve for W2 0, but I cannot solve it directly. I can only solve like if I were to multiply by W1 transpose on the left to eliminate some of the things, right? So I will have negative 2 W1 transpose CXX W2 plus 2 W1 transpose W2 lambda 2 plus lambda 3 W1 transpose W1, which is equal to 0. Okay, and I know since CXX is symmetric, I know that this is, since CXX is symmetric, I know that this is the symmetric of transpose of CXX transpose W1, and I have the W2. So this term I can write as negative 2 W2 transpose CXX W1 plus, well, W1 transpose W2, this becomes 0, right? Plus, and this is 1, right? So I have lambda 2. And also, if I were to recalculate this, I know this is lambda 1 W1. I mean, lambda W1, the greatest eigenvector. So I will get negative 2 lambda W2 transpose W1 plus 0 plus lambda 2, which is equal to 0. So I have this also 0. So I get lambda 2 is equal to 0. Okay. Whoops. How did it become lambda 2? This has always been lambda 3. At some point, this became lambda 2. So I'm carrying this guy. So this is lambda 3. I don't want it to be taken as lambda 2. This is lambda 3. This is lambda 3. Lambda 3. Lambda 3. This is lambda 3. And this is lambda 3 too. Why does this matter? Well, it matters because I can come write this term. So again, with this lambda 3, so W2 star, the best second direction, is at negative 2 CXX W2 plus 2 lambda 2 W, what is it, lambda 2? Yeah, lambda 2 W2 is equal to 0. Well, then the second direction, W2, is also an eigenvector of CXX. And which eigenvector, pray tell? Well, it is the eigenvector. If I were to go and look at this guy, it is the one, if you want to maximize it, you're going to minimize the lambda 2. So that's, sorry, if you want to minimize the error, you would like to maximize the lambda 2. And so the next one is the one that's after the largest eigenvalue. So we found our principal component analysis. So principal component analysis is, I would like to reconstruct my x of et from my z of i's, and I will use several of these w of i's, which are I equals 1 to k, and this time k is less than, hopefully, d, and it doesn't need to be. And these wi's are the eigenvectors of CXX, the covariance matrix of your data set. So you let this eigen the decomposition has something to do with how your data is distributed, right? CXX that correspond to the largest k eigenvalues. So, my dear friends, this was PCA and eigen decomposition for you.